Okay, we have our orientation tolerance symbols that include perpendicularity, angularity, and parallelism. Then we have our profile tolerance symbols, which are line profile and surface profile. They're the same except for we've got a line bridging across the bottom of the surface profile. The symbols are the same. How they're applied are different. Okay, and we have our position tolerance symbol. There's only one of them, and it looks like a crosshair. So whatever diameter the circle is, the crosshairs are 1.5 times the length. And the position tolerance defines the acceptable amount of variation in the location of a feature relative to the true position specified for the feature. And then we have runout tolerance symbols. All of these symbols have modifier tolerance symbols. There's a whole bunch of modifiers. Some of them are used more commonly than others. So they modify the tolerance in the block. And it may be applied to some tolerance specifications. Okay. Now we have this concept of material boundary conditions. Okay. And this is a relatively new thing to use the word boundary. It was in 2009 that boundary conditions were discussed. Before 2009, it was always called material conditions. The semantics is material condition is the physical part you're measuring. What is its condition? And the boundary condition is what is allowable. So it's semantics, but if you talk to someone that's been in the trade for a while, they're probably just going to call it material conditions, regardless of which variation of the term they're looking at. So material conditions is regardless of feature size is assumed if it's not called out. If there's an abbreviation, it's RFS, but it's not required to put it on the standard anymore. If it's omitted, it's if other conditions are not listed, it's assumed that RFS applies. Okay, and we have maximum material condition, which is MMC. Okay, so it's the condition of the part with the most amount of material on it. So if you're looking at a hole, it'd be the hole its smallest allowable size. If you're looking at the overall length of something, it would be its largest possible size because it has the most amount of material allowed. And on the opposite, we have the least material condition. So in the example of a hole, it could be a hole with the largest possible hole allowable by the tolerance, or likewise on an outside shape, it would be the smallest it could be. But it's the condition where you think about MMC would be if you were to weigh the part, it's the heaviest it could be. And if you were to weigh it and it was the lightest it could be, it'd be the least material condition. Okay, the boundary conditions are basically the same thing, but it's not, again, not the physical part, but it's the allowable boundary on the drawing. So we have regardless of material boundary, same thing. It is, if it's not called out, it's assumed that it's regardless of RMB. Okay, and then there's maximum material boundary, MMB, and least material boundary, LMB. Okay, so I'm not sure why they introduced these new abbreviations. Okay, material condition, RFS, regardless of feature size. The default condition and applied tolerance must be met regardless of the size of the unrelated actual mating envelope of the feature size. Okay, maximum material condition, okay, or MMC, it's size limit of the feature that results in the maximum material in the part. And it's indicated by a letter M inside a circle on the geometric frame. Material condition, LMC, is least material condition. size limit of the feature that results in the least amount of material in the part, and indicated by the letter L inside a circle on the geometric frame. Now let's look at boundary condition, RMB. It's regardless of material boundary. It's also the default condition for datum features references, and requires the datum features to be established from the feature surface regardless of the material condition. Then we have our boundary condition MMB, which is maximum material boundary. It's a limit outside material that a feature may extend to as a result of the size of geometric tolerances that are applicable in the feature, also indicated by the letter M inside a circle on the geometric frame. Then we have our boundary condition LMB, which is least material boundary. Limit within the material of that feature may extend to as a result of the size of geometric tolerances that are applicable to the feature, and indicated by the letter L inside the circle. So the boundary conditions will occur only next to datums, and the material condition will be associated with the feature itself tolerance. Okay, modifier symbols used in tolerance specifications. We have translation, independency. There's maximum material condition or maximum material boundary. We have least material condition or least material boundary. We also have what's called a projected tolerance zone, free state, tangent plane, and unequal disposed profile. The ones you're going to see the most common, though, are going to be MMC and LMC. Okay, there's also symbols you'll see on drawings for castings, forgings, and molded parts, and they are specific to those types of parts in those industries. They are defined by a different standards, ASME 14.8. So if you want more specifics about that, you'd have to look up that standard book. But here's some symbols you might see. There's a thing called a parting line. It's where the mold separates, and the resulting part typically has a little seam you can see. That's called the parting line. So there's an symbol that has a half circle, and it says all around this side of the parting line. So if you're familiar with welding symbols, it's similar to that, but it's specific to mold making, and that's why it's a half circle. And then we have another one that's all over this side of parting line. That condition can be met. So you might be texture on an entire surface from the parting line up, and it has this double half arc. And then we have our parting line or parting line symbol, which is a square on end, kind of like a diamond, going to a phantom line. And that's going to define where the parting line is for the part, and the mold maker needs to make the mold so that it separates at that. And it's typically acceptable to have a witness mark or where the mold halves came together. Okay, so here's a feature control frame example. Okay, and it specifies geometric tolerance requirements with all those symbols. And the amount of information depends on the desired level of control. And you read it from left to right when required order for provided information. So if we look at this symbol, the very first box is the geometric control called position, and that position needs to be held to a diameter, and the tolerance on that position is 16 thousandths, and they have a material condition modifier, so it's maximum material condition. And then the ST is a statistical tolerance modifier, typically affects assemblies. And then we have our datum. So they start with A, B, C, and you cannot repeat a datum within a drawing. So you can go all the way through the alphabet. So your primary is going to be the first one. Secondary is the second one called out. Looks like we've got a material boundary modifier next to the B. And then we have our tertiary datum, which is C, and a translation modifier. So that's a fairly complicated frame. I'd say that's probably a little more than I would see on average. Somebody just wanted to throw a bunch of symbols in there for examples. But yes, you read it from left to right. Okay, feature control frame applications to surfaces. Okay, the leader to connect to a surface in an annotated model or orthographic view. We're looking at an annotated model on the left. Here's a bunch of different options. Okay, so you can see the feature control frame. This wouldn't necessarily truly have multiples on a true model. They're just showing the different acceptable positions. So the frames have to be in one of the primary views, and when they are contacting, they need to terminate in an arrow or a dot. So if it's pointing at an edge, it'd be an arrow. If it's pointing at a surface, it would be a dot, as shown on the left. Okay, and here's an example from a orthographic projection, all the different options for putting that same geometric frame. So you can have it go an arrow direct to an edge. You can have it come off a leader line. You can have it come off as a flag. It can be on either side of that leader line, or it can point at the surface and would terminate in a dot. Okay, the feature control frame is related to features of size and threads. So here's a frame, and they specifically want to hold the position tolerance in the first example on top to the minor diameter. So the arrow is pointed at the solid line on the whole feature and not the hidden line for the threads, and it specifically says minor diameter. Otherwise, it's assumed you're going to the what's called the pitch diameter, which is halfway between the minor and major diameter. Okay, so you're going to place adjacent to the size, dimension, or thread specification. And the lower one is the same example. You want it held to the major diameter, so you would call it out that method as shown. Okay, here's another example. The geometric frame can be attached to a dimension as shown in the top, or it can have its own leader line going to the whole feature. Here's two examples of a slot. The position of the slot, you can either have it fall underneath the dimensional text, or you can have its own leader line going to the same dimension. Okay, datum identification. Datum features are the surfaces and features of size used to establish theoretical perfect datums. The datum feature symbol is to identify a surface or feature size as a datum feature. So you're saying, okay, this is my important feature, and then this is where my tolerance needs to be based. Okay, so when you're doing machining, that's where you want to keep track of your datums and your origins. But the symbol itself, whatever your character height is on your text, is X. The triangle shape that attaches to the feature is 60-degree triangle, and then the box that the datum letter would be in is 2 times the font size. Okay, datum features symbols applied to surfaces. So here's some examples of the datums. Okay, so annotated models and orthographic views. You can actually attach a datum to another feature frame. So on the left-hand side, we have datum A actually connected to the parallelism call out of the surface denoted in the left. And it doesn't matter which side of the leader line, if you put it on a leader line, that the datum falls, but it has to be on an edge or a leader line or a geometric frame. Okay, datum feature symbol, application to feature of size. Okay, annotated models and orthographic views, some more examples on the left. You can see several datums. You can have it on a dimension, you can have it on a face, you can have it on a pointing to another frame. It can be called out to a diameter. All of these are acceptable conditions. And there's a thing called a datum target. This is typically used on things that maybe most of the surface is irregular, like a casting, but you have key points that you're going to use as your datum. And those might be qualified or machined, or those areas are held to a tighter tolerance. So the datum target requires a specific locations on the datum features to be used for establishing datums or a simulated datum. They have to be identified by a letter and a number in the lower half, and the target size in the top half. So in the example on the left, it's the second datum target, and it has to fall within a 1/4 inch diameter or 250 thousandths diameter of the wherever it was called out on the drawing. And there are movable datum targets. So this shows a datum target that could move up to 60 degrees and still be valid. Here's some example of datum targets. First one is a datum point, second one's a datum line, and the last one's a datum area. So in that previous example, when you had the 1/4 inch zone, that area would be a 1/4 inch in diameter. Yeah, the datum reference frame. There are 3 mutual perpendicular planes, and axis is to establish a coordinate system. So if you're into machining, this is going to be pretty similar. This is where your coordinate system would be defined. You see this on drawings a lot when they are defining hole patterns by coordinates. But most models will have a reference frame. Created by a datum feature, references in the feature control frame or note, and one part may have multiple datum reference frames. Okay, basic dimensions. They are theoretically exact dimension value to which plus or minus tolerances are not applicable. So it's a number that's theoretically perfect that you then apply the tolerance to. They can be identified by a rectangle around the dimension or a note like the one shown on the left. I rarely see this, but on simple parts you might have a note that say all dimensions are considered basic, and then you don't have to have boxes around them all. Or you could say that all untoleranced dimensions are basic. To me that's a little confusing, because if you're using general tolerances, then it would, you wouldn't know which ones are basic or which ones aren't. So I've only seen it applied to very, very simple parts. And the tolerance shown in the feature control frame or note, and the tolerance is not directly applied to the dimension value.